So as Carol already discussed, species depend on certain climate conditions to survive. So for example, here, this blue oval is representing the space for one species, the precipitation and temperature that they might be able to tolerate. But what we also know is that juveniles have a much smaller climate space that they can tolerate than adults. And so juveniles, especially tree seedlings, they have these really short roots, so they can't get into the deeper soil water like adults. They're also really sensitive to these hot temperatures near the ground because they don't have bark to protect them, so they can get girdled by hot temperatures. And so what this creates is this situation where we might have adults existing on the landscape over here where it's hot and dry, and when those trees established 200 years ago, the climate conditions were different, and so they were able to regenerate. But now they're just hanging on because they're these big trees that are less sensitive to climate, but they can't regenerate. And so what might happen is if we have a fire or another stand replacing disturbance in that area, we might expect a transition to a different vegetation type. And this is what Carol was talking about, how fire can catalyze change. So when we have landscapes that are in this space, we might expect high severity fire that kills the adults to catalyze change because the climate's no longer suitable for those trees to regenerate. And so what we really want to get at is what are those climate conditions that are necessary for ponderosa pine and Douglas fir to regenerate following fire, and how has climate suitability for this regeneration to occur, how has that changed over the past 35 years or so in our sites. So we did this, as I said, for ponderosa pine and Douglas fir, two of the most dominant lower elevation tree species across the whole western U.S. Their ranges are shown there in different shades of blue. And we went to 90 sites across the western U.S. in 4 main regions. So we had 40 sites here in the northern Rockies. We also had sites in the Colorado Front Range, the Southwest, and then Northern California. In all of these areas, we went to fires that had occurred between 1988 and 2007. And what we wanted to do was age all of those trees that had established after a fire to figure out what were the climate conditions like when these trees started growing. So what are the conditions that we need to get trees growing after fire, and what were the conditions like in the years when we didn't see any trees starting to grow. So we went to all of those sites, we destructively sampled all of the trees that had started to regenerate after the fire in small plots. So we're not like digging up all of the trees that are coming back. And we brought them back to the lab. You can see some of these trees, because some of the older fires, they were like this big, so it was a big process to dig them out. They weren't all just seedlings. And we brought them back to the lab so that we could age them precisely. So we needed to know exactly what year did this tree start growing if we wanted to compare it to the climate conditions of that year. So to do that, we cut up our trees into segments across the root-shoot boundary. So right where the tree turns from root into shoot, we aged it right there, and that's the exact age of the tree. And so we did that because you can count branch whorls, or how many branches there are, or bud scars to get an estimate of how old a tree seedling is, but you can't get annual precision. So it was worth all this time and effort to age all of our trees under the microscope so that we could get exact annual precision for all of our trees. And so we did this for almost 3,000 trees. So this was a big 1.5-year long effort in the lab of aging trees. But what we ended up with were 8 structures for each one of our 90 sites. And so what this is showing is just an example of one site where this red line is the year of the fire, and then these bars represent what % of the regeneration that we saw at our site happened in which year. And so what you notice is there's a lot of variability. So for example, we often think the year after the fire is when we see most of the regeneration, but at this site we didn't see any. On the other hand, in 2009, we saw almost 50% of the trees that regenerated started growing in that year. So we are interested in trying to figure out what explains this variability. So we used climate predictors. In particular, we did try to focus down on those seasonal conditions like summer vapor pressure deficit, which is basically a measure of humidity or how dry the air is, so how much moisture it's pulling out of these little seedlings. We looked at soil moisture of the driest month and spring soil moisture, and then also the maximum surface temperature, which seedlings can be really sensitive to. And then we included these non-climatic predictors that we know can also really influence post-fire regeneration. Specifically, these top 2 came out more important for ponderosa, and the bottom 2 were what were important for Douglas fir. And so what we found was that the relationship between these climate variables And the probability of tree regeneration is not linear. It has these very strong threshold effects. So for example, here we have, again, this measure basically of humidity where high values mean it's really dry. And once you cross a certain point, the probability of recruitment in any given year drops dramatically. That was for ponderosa pine. For Douglas fir, we saw a similar pattern, but with the maximum surface temperature. So once that temperature right at the ground level crossed 49 degrees Celsius, which is about 120 degrees Fahrenheit, we saw a big drop in the probability of regeneration. And that sounds really hot, but like right near the soil surface, especially when it's black after a fire, it can definitely reach temperatures like that. We saw similar threshold effects also for our soil moisture measures. So because we saw these thresholds, we were interested in looking at how does the climate at our sites compare to these thresholds, and have we crossed these thresholds or not. And so what we did is we took the climate time series at each one of our sites. So what I'm showing here is each one of those lines is the average climate conditions by region. So that green line represents the average of the 40 sites that we had here in the Northern Rockies. The dashed line is our threshold that we got from our model. And then each one of these dots is a year when the climate dropped below that threshold. So those are the years we would expect the climate is good for regeneration. And so you can see that prior to 2000, there's a lot of dots. Climate conditions were much more suitable for regeneration. After 2000, here in the Northern Rockies and also in the Southwest, we don't see any dots. So that suggests that for vapor pressure deficit, the conditions have become so dry that they're really not conducive to tree regeneration. I should have mentioned earlier that we specifically targeted the hottest and driest sites within each region where these species grow. So this is not representative of everywhere that ponderosa pine is in the Northern Rockies. It's really at the lower limits of its elevation. So those hottest and driest sites near where it's already transitioning into maybe grasslands or shrublands. We saw a similar trend for Douglas fir. It's a little bit less pronounced, but here in the Northern Rockies, it holds true, where we have every time this green line drops below that threshold, it's cool enough that we would expect regeneration. But again, in recent years, we don't see a lot of those dots underneath representing good years for regeneration. So these are just two examples of the climate variables. We also wanted to combine the influence of soil moisture and temperature, or soil moisture and humidity, depending on the species, and see overall how has the probability of getting tree regeneration after fire changed over time. And so we did that by using our model and the annual climate conditions at each one of our sites to predict the probability of regeneration from 1980 to 2015. And we held distance to seed source, fire severity, and time since fire constant. So this is really a measure of climate suitability for regeneration. What you see, there's a lot of variability, but overall, again, before 2000, we see a lot of peaks. After 2000, except for in Colorado, which is that black line, we really don't see many peaks. And so we expect there to be variability because, again, these sites are at the hotter, drier end of where we see ponderosa. So we wouldn't expect every year to be good for regeneration anyway. But what we can really show here is that the failures of regeneration that we're seeing in recent years may definitely be linked to these climate conditions that are really hot and dry and not suitable for tree regeneration. For Douglas fir, we didn't really see trends for the Southwest or California. These lines were pretty flat, but here in the Northern Rockies, we definitely saw a decline in the climate suitability for regeneration over time. And so these are the trends that we saw at our sites in particular, but we also wanted to kind of look spatially at maybe the patterns we might see. And so using a little bit coarser climate data, so this is climate data at 4 kilometers, we mapped where we would expect to have regeneration in the Northern Rockies in particular. And so just a little bit of background of these maps. This is showing the number of suitable years that we'd expect for ponderosa regeneration, 1986 to 1985, compared to the most recent decade that we had climate data for, 2006 to 2015. Those black outlines are all the wilderness areas. So you can see that we don't have the Bob Marshall actually mapped because the layer that I used to clip this by the ponderosa pine distribution, for some reason didn't think there was any in the Bob Marshall. But if I went back and I checked that area, and all of those areas are blue. And so what the blue colors are showing are areas where most of the years are suitable climatically for regeneration. So we expect those areas to have regeneration. When you start to see some of these red areas, particularly near Boise, and also along the Salmon River in the Frank Church, and also the Selway River in the Selway Bitterroot, those are areas where we only see a few years per decade in the most recent decade where the climate was suitable for regeneration. And so those are areas where we might expect there to be changes in the future. Because regeneration depends on a lot of things, not just climate. Like, for example, ponderosa pine doesn't produce a good cone crop every year. So if you only have 1 or 2 years per decade that are suitable climatically, you also need that to line up with a good cone year and some other factors. And so it might be increasingly difficult to see regeneration in some of those areas in the future. Just to give you an idea of where we're seeing the most change over time, this map, I just subtracted those 2 maps. And so the areas that are actually impossible to see that are in light blue, like in Colorado, are where there are no changes over time between those 2 decades. The areas that are in red, so again, particularly in the Selway Bitterroot, the Frank Church, also down near Boise and near Missoula, those are the areas where we saw the most change over time. So just in a 20-year span, we saw a difference of about 4 or 5 years per decade, fewer years that were suitable for regeneration. So that's a pretty significant change over a short amount of time. I also want to just highlight that in our models, these other factors were also really important. And so what this is showing is the relative influence of each of these factors on whether or not we see regeneration. And so climate for ponderosa pine, for example, its relative influence was like 25%. That big green area is distance to seed source. And so we all know that this is kind of expected for ponderosa pine to be so important because its seeds are big, they don't disperse very far, so you definitely need a seed source nearby to get regeneration. Even more important than it was for Doug fir, which seeds are a little bit smaller, they disperse a little bit farther. What was also really important for ponderosa pine was fire severity, which is this blue, dark blue area. And so that was important even after accounting for a distance to seed source. So often we think high severity fire, we see less ponderosa regeneration because it's just farther to the seed source. But even with a seed source, we saw that fire severity had a negative effect at our sites on ponderosa regeneration. And then for Douglas fir, we saw that climate was a little bit more influential, and then time since fire really mattered. But that's mostly a function of our sites in the southwestern California, where all of the Douglas fir established within about 3 years of the fire. Most of our sites here in the Northern Rockies, we saw much more continual regeneration, up to about 15 years after the fire. And then one other point that I just want to bring up is that wildfires can really alter the microclimate conditions of a site. And so we put out temperature sensors in the Lolo Peak fire, which happened in 2017 right near Missoula. And so this is the summer after the fire. And this is the green line is an unburned area compared to moderate and high severity areas right nearby of the same aspect, same elevation over time. And what you see is that the maximum temperature, especially in July and August, the hottest time of the year, can be almost 10 degrees warmer in these areas that burned at high severity. So this is just another factor to consider when you're thinking about whether or not there'll be regeneration, because 10 degrees, if you compare that to our plot here, that's definitely enough to push you across the threshold to these conditions that might not be suitable for regeneration. So it's possible that there are sites on the landscape where you were maybe seeing Douglas fir regeneration in the understory before the fire, that because of the microclimate conditions created by the fire, then you won't see any regeneration just because it's so hot without that canopy cover. So overall, what we found was that some of our low elevation forests have already crossed these climate thresholds for recruitment. And so in those areas, if we have high severity fire, we would expect there to be transitions to a different type of vegetation, as Carol was discussing. However, because fire severity was really important in our model as well, and because it affects both seed sources and cooler microclimates, reducing fire severity can definitely have a positive influence, or it can increase post-fire regeneration. And so this is just another example of why it's so great that you have active fire regimes in these wilderness areas because, as we've talked about, when you have multiple repeat fires, there's more variability, less of these really big high-severity patches, and so that's helping all these other things that we've already talked about, but it's also helping post-fire tree regeneration. So it's just one more reason why having a lot of active fire in the landscape can actually be good. But in other situations, we might just have to accept that we will have transitions to non-forest vegetation. So this is a site, again, on the Canyon Ferry fire. That's the reservoir right there in the background, where we, 17 years after the fire again, south-facing site, we didn't see any trees coming back, even though there was a seed source nearby. And so at this point, it seems unlikely that a huge amount of regeneration will occur on that site. So thanks to everyone who helped, and I just want to point out that this was also funded by the Joint Fire Science Program that we were talking about.
We saved time for a question.
Okay, great.
I was just wondering, in the map where you showed where you subtracted the two,
Yeah.
and there's that distinct difference between the Colorado sites and the sites around here.
Yeah.
Do you have a sense of what accounts for that difference?
I think that the sites near here are just closer to those thresholds, and so even if they, like the sites in Colorado and the sites here both got a certain amount warmer, our site, the sites in Northern Rockies crossed the threshold, the sites in Colorado didn't. And this is like, there's a lot of higher elevations. You can see right on the front range where it's lower elevation, there was change. So, whereas here we have a lot of topographic complexity, and I think that that's contributing to the more varied spatial pattern that we have in the Northern Rockies.